All right. We saw that there are challenges with the return ratio, right? In the usage of that. There are limitations of return. Return ratio and asymptotic gain formula is very useful, but the return ratio itself, since not being a function of, not being an invariant of a single loop, would pose a challenge in terms of if you wanted to use it, for example, in terms of determining the stability of the system, which one would you use? Because you saw that, for example, in the examples that we saw before, that for different sources you can actually get different return ratios. So the question is that which one is the one that you use for stability analysis, right? And there's a way to get around that, but perhaps there's a better way. Now, the question is that, what are we trying to define when we define the loop gain? We saw also that the loop gain, we defined what we call the unilateral loop gain. Unilateral loop gain being essentially a loop where the signal flows in one direction, right? It can only go in one way. And the question is, how do we go about defining a general loop gain that's an invariant of the loop? So now, what are the properties that this loop gain should have? Well, let's think about what we really need to have. We need to have, let's look back at the basic picture of the feedback, very kind of system level picture of the feedback that we had before. So you have this A, and you have F, and you had a UI plus and UI minus. Well, this is kind of a semi-circuit viewpoint. But so you have something like this. Now, if we determine the transfer function of this thing, right? The closed loop transfer function of this thing, H meaning Y over X, was A over 1 plus AF. This is a very famous, very well-known equation that we are all familiar with. So, and if we saw that if we broke this loop, right, and applied a signal Ux and looked at what came back as Uy, that ratio was basically, we can define this as loop gain, which was, we defined the negative of that as a loop gain, Uy over Ux, which was AF. So we see that our loop gain, if we want to define something as loop gain that's general, it should hold in something like this. So in other words, the transfer function that, for the closed loop transfer function that it produces, should have a denominator of 1 over 1, of 1 plus loop gain, 1 plus t. So that's one of the things that it should look like. But what else do we know? What is the denominator of a transfer function in general for a circuit? What is the denominator of a transfer function? Say again? Product of the pole. Yes, exactly. It's a polynomial with roots that are the poles, right? Exactly. It's product of the polynomials or monomials. But we also know that that's related to something from the nodal analysis, right? If you think back all the way to nodal analysis. You remember what this transfer function had in its denominator, right? It was the determinant of y, right? The y matrix. This is from nodal analysis, basic network theory, right? So the roots of the denominator, the poles of the system, were the roots of the determinant of y, right? Determinant of the y matrix, the admittance matrix of any network. We know that from the basic circuitry. So this means that the roots of this should be the same as roots of that. In other words, however we define the t, this condition should hold. So if we say 1 plus t equals 0, it should mean, it should be necessary and sufficient condition for delta being 0. So this is a condition that whatever we define as the loop gain should hold, should satisfy. Otherwise, it would not produce the same roots. Otherwise, it would not produce the same poles for the transfer function, right? So this is a condition that it needs to satisfy. So this needs to hold for whatever we define as the ratio. The other things that we want for a loop gain to be meaningful is that it should be an invariant of the loop. It shouldn't matter if you have a single well-defined loop like this. No matter where you cut it and how you cut it, you should get the same result, even for a bilateral loop, right? And we saw that for unilateral loop, we have already we determined what it is. I mean, right? It was basically 1 over the reciprocal of the loop for the unilateral loop gain was the sum of the reciprocals of the voltage loop gain and the current loop gain, forward loop gain. But now what if you have bilateral loop? Basically, a loop where the signal can also travel in this direction, in addition to this direction. So it can go both clockwise and counterclockwise. What would we do and how do we modify it? So we will do a little derivation here to find out. Now, the second condition is that this should be invariant. The third, it's not a requirement, but it's a desirable thing, is that it should be easy to calculate, at least conceptually. It should be easy to say, okay, this is the procedure you apply to calculate what this loop gain is. Now, for the unilateral loop gain, we had a relatively straightforward calculation, right? So how did we calculate? We said, okay, one time you apply a voltage source here, you apply a Vx, and you leave this open circuit, and you measure Vy, right? So we defined the forward voltage loop gain as the ratio of negative Vy over Vx when Iy was 0, meaning that this was open circuit, right? And then we said, okay, now also apply a current source. You could also apply a current source, Ix, and short circuit this and see what is the current coming back, Iy. And that ratio, we said, was the forward current loop gain. When Vy was 0. So we had these two things defined. And then we saw that if your loop was unilateral, what you had was that the total forward loop gain was 1 over the forward voltage gain plus 1 over the forward current loop gain. But that was for unilateral. So this is for unilateral. Unilateral loop, which basically means that the looper signal only, in this case, can go in the clockwise direction. So now we are going to try to generalize it to a case where it can go in both directions and see what it looks like. So how do we do that? Well, for this, we really draw that equivalent two-port network and do it for a generalized two-port network. So we are using this for derivation, not for really our analysis or design. So let's say, look, what is the most general two-port that you can have? You can have an impedance or admittance Y1. You can have signal trap flowing in both directions. So you have a dependent source at the input that depends on the output, and a dependent source at the output that depends on the input. And your feedback network in general also is bilateral, meaning that there's a signal flow from the input to the output and from the output to its input. So let's call this Y1, let's call this Y2, Y3, and Y4. And then this is G1 VO, if this is VO. And this would be G2 VI. This would be G3 VO, yes, because it depends on that, if this is the VO. So let's connect this to ground like this and close the loop like that. And here, and you can even think about having some sort of a source, I in here. So this is G3, so this is VI and this is VO. And this would be G4 VI. So what these four admittances represent are the admittances of the port. In general, you can have any admittance here. They can be functions of frequency. And then these transconductances show basically the signal flow in both directions. So with these, you can see what are the transconductances that are responsible for your forward loop gain. Which two are the ones that are responsible for the forward transfer, the flow in the clockwise direction? G2 and G3, right? This guy and that guy, because this takes the signal from the input to the output, and this takes the signal from the output back to the input. And G1 and G4 are responsible for reverse. So if you set G1 or G4, or either one of them to 0, your loop becomes unilateral. right? So the loop is bilateral if you have all 4 of these, because the signal can flow in both directions in general. So if you take this and say, okay, I want to find out what is the relationship between V in and V out, right? There's a simple way of doing that. You can write KCL at the input and output. You're basically writing the nodal analysis, doing nodal analysis, right? So here, you know the sum of these 3 currents is 0. So you know that the current going through here and that current are the same. So what is the current going through here? It's Y1 VI plus G1 VO. So this is the derivation that we are doing for the bilateral loop gain. Then you get this part, Y3 VI plus G3 VO. All of these 4 currents are equal to I in. And then for the output, you don't have a source, so it would be 0. Similarly, it would be Y2 VO plus G2 VI plus Y4 VO plus G4 VI. Okay? And then you can simplify this. You can basically write it in this form. You can write it as YI G GI GO YO VI VO equals I in and 0. And what we mean by these are defined as, so YI is basically the sum of these 2 admittances. YI is Y1 plus Y3. YO is Y2 plus Y4. GI is G1 plus G3. And GO is G2 plus G4. I'm just writing it in a compact matrix form. That's the Y matrix. This is the Y matrix, right? This is Y V equals I stimuli that we've seen before in circuit analysis, network analysis, okay? So now what is the parameter that matters? The determinant of Y, right? Delta. So what is delta? So delta, if you write delta, is basically the determinant of this thing, which is YO minus GO. And if you want to really expand it, you can expand it in these forms. So it would be Y1 plus Y3 times Y2 plus Y4 minus G1 plus G3 minus G2 times G2 plus G4. Okay, whatever. All right, so now the key question is, how do we relate this to the parameters that we want to actually measure? So what kind of measurements are we going to be doing? So before we had several different measurements, right? We had the measurements of, we had 2 measurements before. When we did these 2 measurements, let's calculate these 2 quantities quickly. We'll do one, and I will quickly write down the rest of them because they're calculated in a similar fashion. So I don't want to go through all the calculations. It's in your handouts and pretty straightforward. So let's calculate, for example, TFV, right? The forward loop gain, voltage loop gain. How do we do that? We break the loop, right? We broke the loop here, for example. Right? We applied, if it's a forward, we have to basically apply a voltage here. We apply a Vx, and we measure a Vy, right? Oh, we measure Vy. So this is Vx, and we measure Vy. This is what we did, right? So you can calculate this. It's pretty straightforward. If this is Vx, then this is going to be now Vo is going to, this is going to become Vx. This is going to become GmVx, right? Because it's the Gm times this voltage. Now it's Vx. So it's GmVx driving here, but that still remains Gm. So now this is G1 Vy. So if you take these 3, you can write 2 equations, right? It's simple. You can write an equation here at the input. You can say, what is the sum of the currents? The sum of the currents would be, so if I write that equation, for example, you have, and this is in the absence of I in. So I in is not going to be here because this is just nulled. I in is nulled. So you have GmV3, okay, plus, sorry, GmV Vx plus G1 Vy, and these two is equal plus, now this is Vi, right? It's Yi Vi, which is the sum of, Yi is the sum of these two. That's the current through both of them is 0. So that's one equation. It's a KCL written here. And then you can write a KCL here, which basically says G2 Vi plus Y2 VO equals 0. And YO now is basically YY, VY, right? So those are the two equations. This is the KCL on this node, the second equation. So you can easily see that you can eliminate VI between these two equations, and you get the relationship between VY and VX. And when you do that, you will get this. So you get, when you do that, you will get T, the forward voltage loop gain, defined as negative Vy over Vx when Iy is 0 equals negative G2 G3 over Yi Y2 minus G1 G2. And similarly, if you do the same thing, now instead of a voltage source, you apply a current source and you short circuit this one. You can write another set of KCLs, and then you get TIF, which is defined as Iy over Ix when Vy is 0. This is going to be shorted in that case. And you measure the current through that. And then that would become G2 G3 over Yi Y4 G3 G4. So those are those two. And if you calculate now, if you take these and calculate the 1 over the reciprocals of these, TVF plus 1 over TIF, what you get is negative Yi Yo minus G1 G2 minus G3 G4 divided by G2 G3. So you get that. Now you look at that and you compare it with the delta, right? Because you want to see if I can express it in terms of delta. So if you look at the delta, you can see that this is simply negative delta plus G2 G3 plus G1 G4 over G2 G3. Now the question is that, is this the full forward loop gain for a bilateral loop? Right? So for it to be the forward loop gain, this is, we need to satisfy this condition. Does it satisfy that condition? This condition means that if the forward loop gain is negative 1, your delta should be 0, right? If this is negative 1, then this becomes 0, right? So if I set this TF to negative 1, the right-hand side of the equation becomes negative 1. So it means that there's a minus sign here. So this thing should be, so this should imply that if this is 1, if you set this to 1, it should say delta equals 0. Does that? No. Why? If I didn't have this term, do you agree that it would imply that delta is 0? Because then, if you want this to be 1, and this is G2, G3, G2, G3, if this wasn't there, then it means that delta has to be 0 for this to be 1. So this is the term that's causing trouble. And look at that. That term would be 0 if G1 or G4, if either one of them is 0, which means that the loop is unilateral. Right? Because if G1 or G4 is 0, it means that the signal will only flow in this direction, because the other direction will be killed by one of these guys, which is consistent with what we saw. So it means that this is insufficient. There's something missing in that. There's a correction factor. And that correction factor is right in front of our eyes, right? That correction factor is what? This is the correction factor, right? If I add this correction factor to this term, then I will have the correct loop, the definition of the loop gain, which for bilateral. Let me write this down here. So it means that my overall loop gain, forward loop gain, is 1 over the forward voltage loop gain and 1 over the forward current loop gain, plus this other term, right, that I have to find what it is, right? So if I add this G1, G4 over G3, G2, or G2, G3, then that's the correction factor. So that's what I need to add. But the question is, what is this quantity? What is this quantity? Because this is useless. I mean, it's fine, but it's useless for analysis and especially for design. Because those things we know how to calculate. This thing we don't know how to calculate. What do you do in a circuit? G1, G2, G3, G4. This is like some abstract. So unless you want to fall back on this like two-port analysis, which is really not the way to do circuit analysis, in the feedback analysis. I mean, you can analyze, but you can't design based on it. So you can do whatever you want with it, but it's not useful. So what do we do? What is the solution? Well, there is a very interesting solution to this, which is that if you actually look, you remember how we calculated these two, right? I'm going to redraw it here. So you have a feedback, you have an amplifier, UI plus and UI minus, and then you have the F, right? And then you had the X and the Y. And we said, we broke the loop here, and for those two quantities, once we apply the voltage source here, we measure the forward voltage gain, and once we apply the current source here and short circuit this and see what current comes back, right? But now it should give us a clue. What we're trying to calculate should give us a clue what are the other two calculations that we need to make. Because we are really relying on things that depend on the reverse flow of the signal. So for these, perhaps if we calculate these things, apply a Vy here and measure Vx here, or similarly, so I'm just going to draw that part of the circuit, apply a current source Iy here and measure the Ix here. So these would be reverse voltage and current loop gains, right? And these can be calculated. I mean, we know how to calculate. So let's call this VRV, defined as Vx over Vy when Ix is 0, and TRI, which is defined as Ix over Iy, or with a minus sign, Iy when Vx is 0. Now, be careful. These two are not the inverses of those two, right? Because there's a different condition. In these, this one's open and this is shorted. And in the forward ones, this side is open and this side is shorted. So there are 4 different quantities, really. So now if you calculate these things, the question is, what are you going to get? So similar to our previous calculation, you can actually determine this in terms of G1 and G2 and G3 and G4. So I'm going to just write the results, because it's the same process. You just need to write 2 more sets of KVLs. And what you see is the following. You see that TV, the reverse voltage loop gain, is negative G1, G4 over Y1, Y4 minus G3, G4. And the reverse current loop gain is negative G1, G4. You can see now it depends on G1 and G4. If either one of them is 0, this becomes 0, as it should, because these are reverse loop gains, right? G2. So you see these, and you have those previous ones, the forward ones. And if you look at these 4, you see an interesting property. You see the following. If you look at them, look at these 4, see TVF times TVR equals TIF times TIR. So the product of the forward and reverse voltage gain is the same as the product of the forward and reverse current gain. And then, if you look at that, if you look at the term we are trying to calculate, this term, you easily see that that term, G1, G4 over G2, G3, is simply TIR over TVF, which by this expression, by this equality up there, is going to be also TVR over TIF, which leads you to the final result. The final result being the forward loop gain is 1 over the forward loop gain, or reciprocal of the forward loop gain, is the forward voltage gain, 1 over forward current gain, which is the part that we had, these two parts we had before for the unilateral. And there's a correction factor because of the bilateral, which is TIR over T, which you can write it two different ways. You can write it as TIR over TVF or TVR over TIF, whichever one helps you better, works better for you. So you really need to calculate three things. If you want to exactly calculate this thing, is basically the two forwards and one of the reverses, because of that equality, because of that identity. This is true for bilateral. And this is an invariant of the loop for a single loop. Bilateral forward loop gain. And if for some reason you were interested in the reverse total loop gain, so this becomes R, this becomes R, R, this becomes F, this becomes R. Okay, now that was probably one of the hairier derivations that we had. But it's good to know that now you can actually analyze any loop gain forward in general. And this satisfies all three of those conditions that requirements that we set for self. For this, if actually this loop gain is -1, it means that the transfer function will, the roots of that would be the same. The roots of 1 plus t equals 0 are the same as the roots of delta being 0, the determinant being 0. So you get the correct poles, always. It also is something that satisfies, it's easy to calculate, and for a simple loop, it's an invariant of the loop. Doesn't matter where you calculate. Now, a lot of times, you basically just drop this term. You can see, okay, if my reverse loop gain is smaller than the forward loop gain, if this factor is small, if the ratio of these things is small, then you know this is not going to be a major participant in this, right? So you can actually look at that and see what that determines, or what it tells you, a lot of times. And we can do an example of this thing with, I mean, there's an example in your handouts for the actually seeing how this is applied, so as a function of frequency. And I let you look at that. If you have questions, let me know. It's basically just like you're doing something similar as a function of frequency. We are just calculating now that we break the loop, and then we apply signal from the output and look at what comes out in the input. And that comes back basically through the parasitic capacitors. Right? The example you have in your handout is basically this example. So if you have something like this, you can have an R1, an R2, or R3 and R2. So you can basically, you can break the loop here, and then you apply a voltage source and a current source, and then, or you can then apply the reverse and see what comes back through the system. And from that, you can calculate the overall loop gain. And that's the quantity we need to really evaluate for stability analysis, which is what we'll do next. Any questions on this? All right?